volumetric things. Please go ahead.
So,
please unmute yourself.
okay, can you hear me?
Yes, please go ahead.
Okay. So today I'm gonna present VisNerve efficient multidimensional neural radiance field representation for visualization synthesis of dynamic volumetric scene. So our motivation begins with the challenges involved in large-scale simulations. So these simulations incur significant computational cost and generate a vast amount of volumetric data that leads to high storage demands. And additionally, the size of data also introduce I/O bottlenecks during both saving and loading processes, which makes visualization less efficient. So we have seen existing works that handling those challenges by visualization generation. But for these methods, for example, DN Wolf's InSituNet, GAN VR, they all require more than 10,000 images, and video surrogates would also require the original volume data. So their high data requirements makes them these methods less practical, and also they need long training time, which range from more than 10 hours to more than 1 day. And due to the lack of 3D awareness, the images produced by these methods tend to be low fidelity and low resolution, and also limited the camera views because they're only doing interpolation between training views. So our methods also inspired by based on NERF, and NERF is basically just representing 3D things using neural networks that learning to model the scene from multi-view images and model the scene's appearance and geometry. And so this type of model can render photorealistic images from any viewpoint from the scene. So our VisNerve also adopt factorization technique that's inspired by TensorF and only require 42 images for each scene frames. And we also work with higher resolution and actually like arbitrary resolution because we are using volume rendering. So, and we achieving faster training speed, which only taking like 1 to 3 hours with superior generation quality. And also we support parameter space exploration over time steps, ISO values, transfer functions, and multiple simulation parameters. And our main structure uses a hybrid design, which combines implicit MLPs and explicit feature grids. So in this design speed up the training and the inference, and also improve the generation quality because we have like better expressiveness from the combined structure. And we factorize the spatial feature into matrices and vectors so that we can reduce the complexity from ON cubed to ON squared. And in that way, we are reducing the model size and the GPU memory cost. And we also factorize the feature grid into vectors so that we're reducing the complexity for the parameter space from OM to the power of K to OM. And in that way, we're able to represent a scalable multidimensional parameter space with minimal model size overhead. So for the loss functions, we use the reconstruction loss, which is simply MSE between predict and ground truth colors, and also L1 norm loss to reduce overfitting, and total variation loss to encourage smoothness. So with the regularization, we're able to see that the produced images are like more smooth compared to the one without regularization. So this is evident also in the feature matrices, which with no regularization, we will see much more noise. And for the results, the first one is interpolated between time steps using the 5Jet dataset. And for this nerve here, we're having the highest PSNR, SSIM, and the lowest LPIPS, which suggesting the best generation quality. And also rather compact model size and the fastest training speed, but it suffers from the slowest rendering speed due to the use of like volume rendering instead of just generating the image directly from the model. So from this example, we are able to see that this nerve generating the result that closest to the ground truth and are very consistent in different views at in this animation. So similar results we can also conclude when we are using this for interpolating between different ISO values using the Tangar dataset. And for the qualitative comparison here, we're also seeing the least errors in all views among this method. And we are also doing experiment on like interpolating between different transfer functions. It's actually just like changing the transfer functions. For the first one, we are changing the opacity of two transfer functions. And the second one is more like we're moving the spikes of the transfer functions. So the images would also appear as the changing the both the visible area, also the color. So as you can see, the first one, we can see the opacity of two regions are changing. And for this nerve, we observe very low error in this case. And also in another example here, you can see the change of color and also visible regions. And the last example is interpolating between simulation parameters using the next dataset. We compare it both in direct volume rendering images and ISO surface rendering images. And for the first result is direct rendering images. We're able to see that this nerve also producing a very high quality result, even we are handling like three changing simulation parameters. And the same for isosurface rendering. So in summary, this nerve achieves very impressive speed up compared to both nerve and TensorRF. And beyond this, we also enable scalable and efficient dynamic scene representation, which nerve and TensorRF cannot do. And we also control the model size to be like very manageable, even like we have more like changing parameters. But we still seeing like apparent limitations in this work. So first, when we select sampling views, we not consider optimal view selection, which potentially would improve the training generation quality. We also didn't use flexible number for of views for different scene frames, so which potentially we can reduce the number of training images and boost the model convergence because we're using a smaller training set. And we also didn't optimize for isosurface rendering because for NERF, it's unlike implicit surface representation, which consider more the thing as a surface. So in the future, we might combine this with surface representation methods, which could improve the quality for the isosurface rendering. And the last one is the slow rendering time. So we're considering in the future combining 3D Gaussian splatting with VisNerve framework to enable multi-dimensional dynamic scene generation in real time. So that's it for the presentation. Thank you.
Thank you. So any questions from the audience? Please go ahead, use the mic.
Yeah, a very nice talk. So I was wondering if you considered comparing your work with other NERF-based approaches. So there are several other NERF-based approaches where real-time high-quality rendering is possible. For example, KiloNERF. So have you looked into those and see how your method compares against others?
Yes, we have included such experiment for static scene generation in our appendix, and it's basically for those type of methods. When we are working on this, is just lacking of multi-dimensional works that have been available, like in the field. So we're unable to compare them in for the dynamic scene generation, but only compare them for the static thing. Yeah, is that answering what you're asking?
Okay, thanks.
Right. If there's no more question, we'll move to the next speaker. Thank you again.
Thank you.
So our next speaker is also online. Mai-Zhe Yang from University of Notre Dame is going to present meta-INR, efficient encoding of volumetric data via meta-learning implicit neural representation. Please go ahead.
Yes. Hi, everyone. I'm Mai-Zhe, or Michael, a current undergraduate student from the University of Notre Dame, and today I'll be presenting our work on meta-INR, efficient encoding of volumetric data via meta-learning implicit neural representation. So a brief recap on implicit neural representations, or INRs. They have gained a lot of attention recently for representing volumetric data by mapping spatial coordinates directly to voxel values using neural network. It has the great benefits of having high compression efficiency while retaining very high resolution reconstructions. However, a major limitation is that training an INR from scratch for each volume is typically very slow, is redundant, and offers no reusability across structurally similar data. So this inefficiency becomes a bottleneck for large time varying or ensemble data sets where many volumes share similar structures, but still requires its own separate training for each frame. And there's limited parameter interpretability or reuse. To address this, we propose meta-INR, a meta-learning approach that enables fast adaptation and enhanced interpretability for encoding volumes. So meta-INR is a two-stage pipeline. We have meta pre-training, where we conduct pre-training on sparse subsample volumes to learn a shared initialization. And then next we have volume-specific fine-tuning, which adapts this initialization to full volume data in just a few gradient steps. The key idea is to simulate fast adaptation during training using meta-learning, so the model learns to adapt quickly during the later fine-tuning stage. So during meta pre-training, we use downsampled data, both spatially and temporally, totaling to less than 1% of the original data to obtain a shared initialization between structurally similar data. To do this, we apply a MAML-like algorithm or model-agnostic meta-learning with inner and outer optimization loops to train the meta model. The results is a set of parameters that can quickly adapt to any volume in a dataset, offering a strong starting point for reconstruction. So from this prior, once pre-training is done, we switch to volume-specific fine-tuning, where we start from the learned initialization and update the parameters using the full coordinate voxel values for a target volume. So because the model already has a good prior, it converges quickly with just a few gradient steps, saving time while still achieving high fidelity reconstructions. So to test meta-INR, we ran it on 6 different data sets ranging from small to large, and we included both time varying and ensemble data sets. Our baselines are Siren, which is the original INR network trained from scratch, and also pre-trained Siren, which is similar to our meta-INR model, but instead we trained it on the subsample data without the meta-learning. It ended up not being a very good model, as in it failed to capture a good initialization that can provide fast adaptation. So quantitatively, meta-INR consistently outperformed both baselines across all of the datasets. For example, achieves higher PSNR values, it has better LPI-PS values as well as chamfer distance. And overall, more importantly, I guess, meta-INR performs much better in terms of encoding time, where it trains on average 5.87 times faster than Siren. So qualitatively, in volume renderings, we see that meta-INR performs very well, often even better than Siren, which trains each volume from scratch. Here we see pre-trained Siren was unable to obtain a very good results because it lacked the fast adaptation that is required for a good prior. And the same story can be said on isosurface renderings, where we see on this relatively tough data set, meta-INR performs the best out of all 3. So moving on to another more exciting outcome of meta-INR is that it has improved parameter interpretability. We used the earthquake dataset and projected the model parameters into 2D space using t-SNE, and the result revealed smooth transitions over time. So here is our results from meta-INR compared to, for example, Siren, whose values are non-interpretable because you train each one from scratch and there are a lot of noise during training. For meta-INR, you start from a common prior, which gives each fine-tuning stage meanings as to which direction the model decided to go with. So here we see that the model forms smooth curves, and for each time step, they form continuous loops. So another experiment we did is simulation parameter analysis, where we use t-SNE on the NICS dataset, where simulation parameters vary. So for example, meta-INR's adaptive parameter clusters meaningfully demonstrated the differences in different parameters, such as H0, which at a lower value is at the more left region of this curve, whereas if you increase the value, it will be at the middle region. And similar story can be said about the inner and outer loops for this other parameter as well. So here is another demonstration where we see that when we fix a volume here at the top, as we move further and further away in this curve, the model gets increasingly distinct, which means that our meta models have is interpretable where it projects into t-SNE.
2 minutes.
So for future work, we aim to incorporate continual learning, which to support incremental adaptation during training, and also grid-based INR structures, which can improve scalability and spatial efficiency. And also we want to incorporate transfer learning, which can enable cross-stack generalization across variables in multivariate datasets. In summary, meta-INR is a meta-learning framework for INR that dramatically speeds up encoding, maintains high reconstruction fidelity, and enhances interpretability. It generalizes well across datasets and supports advanced tasks like time step selection or simulation parameter analysis. Thank you so much. And any questions?
Thank you. So any questions from audience? Yeah, please go ahead.
Hi, very nice work. So I had one quick question. So you mentioned in your talk that sometimes you found that your meta INR performs better than training a independent model from scratch without doing the meta learning. So can you give some insight about why is that?
Yeah, so by training each model from scratch, you only have a limited time for each individual time step, as opposed to for meta-INR, we spend a significant amount of time doing the pre-training on large numbers of volumes inside the dataset where it can learn generalizable structures or similar patterns that can then be adapted quickly during the fine-tuning stage, where we see that it performs better than training from scratch. Yeah.
Okay, thanks.
Okay, all right, we'll move to the next speaker. Let's give the speaker one more. Thank you very much. All right, so the final presentation today in the session is by Junpeng Wang from Visa Research, and he's going to talk about visual attention exploration in vision-based Mamba models. Please go ahead.
Can you project the screen? Okay, get to start. Thank you for the introduction. My name is Junpeng Wang. I'm a research scientist from Visa Research. On behalf of all my co-authors, I'd like to present to you visual attention exploration in vision-based Mamba models. So I'd like to get started with some background about Mamba. When we talk about the sequence modeling, there are two popular machine learning models. One is called RNN, recurrent neural networks. The other is transformer. For RNN, the training is slow because RNN processes tokens sequentially, and there are dependency between those tokens. But the inference time for RNN is fast. But RNN also suffers from this significant forgetting issue. For transformer, the training is fast because the training is just a matrix multiplication, which can be massively parallelized on GPU. But the inference time is slow due to this quadratic computational complexity. The performance of transformer currently is still the best. So Mamba was introduced in 2023, and it's actually good across all three columns. And it's also considered as a potential replacement for transformer, especially when the sequence lengths get very long. So within this short talk, I won't be able to explain what is Mamba in detail. But to understand my talk, you just need to remember two things. First, similar to RNN, Mamba still processes tokens sequentially or recurrently. That means there are token dependencies. Second, each input token has two learnable weights, and that can mimic the attention mechanism similar to transformers. With this, let's directly jump into vision Mamba, which is short for V-Mamba. So similar to vision transformer, we also divide the image into a lot of smaller patches, and those patches will be chained into a 1D sequence and feeding into the Mamba model. So in vision transformer, we will learn an N by N attention matrix, which is telling the attention strings between all possible pairs of image patches. But in vision Mamba, we learn this in a different way. We just learn two vectors, C and B here, which are in the shape of N by 1. You can imagine this is much easier to learn than learn this n by n matrix directly. And then after we learn those two vectors, we just do C multiply B transpose. We also get a n by n matrix, which has the same functionality with the original attention matrix in the transformer. As I told you earlier, right, this vision Mamba process tokens sequentially. That means for each patch, it can only see the patches before the current one. Like for the red one, it can only see the patches scanned through by this blue scan line. In order to make this patch see all the rest patches, we can scan the patches in the reverse order. So when we reach this red patch, we just average the two attentions from the two directions. In fact, for Vision Mamba, it's actually using four-way scan to take care of both horizontal and also vertical locality. So this animation will show you the 4 routes of those 4 scans. And at each patch, we just average the attention from the 4 directions, and then we get the attention. So the first contribution for this paper is we introduced 3 new patch scanning orders. The first one is called the diagonal order. You can see we just scan the patches along the diagonal line. So this will make sure the patches along the diagonal line can maximum maintain the spatial locality. Second one is called this Morton curve, or the Z curve order, which is well known for maintaining the spatial locality. And the third one is called the spiral order, which just scan the patches following this spiral circle. You can imagine the innermost patch will have the best spatial locality. So what I have told you so far is only happened within a single Mamba block. But for Mamba model, we will have multiple Mamba stages. And within each stage, we will have multiple Mamba blocks. So the concept of stage and block is similar to the concept of layer and height in transformer. And we have 2 research questions. The first one is, are the attention patterns consistent across different Mamba blocks, which we call the inter-block attention pattern? The other is, within a single block, how is the attention spatially distributed across the patches, which is intra-block attention pattern? To save time, I will directly tell you, for the first question, we found that the attention pattern in different blocks are very different. And then let's focus on the second question. What is the attention pattern within a single Mamba block? So let's assume we divide this image into 16 patches, 4 by 4. That means we will learn an attention matrix, which is set by 16 by 16, right? And using dimensionality reduction algorithms, I can reduce this to 16 by 2. 16 are the 16 patches, and 2 is the 2 coordinates. And using this, we can visualize it as a scatter plot. And we can use a point size and color to denote the row and column of the corresponding patch. So if you can see on the lower left, this image are the patches from the stage 1 block 0. Obviously, we can see a lot of small clusters. And if we highlight those clusters, you can see those are the patches from the same row or the same column. So basically, this is telling us patches from the same row or same column will share the similar attention pattern. And when we click individual patch, you can see patches in this block will always attend to patches before the current one. I can change to different patches. You will see the pattern still remain, right? It's always attend to the patch before the current one. And the word before is defined according to the cross-scan order I mentioned earlier. Basically, this is the cross-scan order. Okay, so if we change to other blocks, the attention pattern will be different. But let's just focus on this. Just focus on this block, and let's see the 3 new orders we introduced. So here's the scatter plot, and you can see that spatially closer patches will fall into the same cluster. Let's focus on the first one. This is the diagonal order, right? If you look at this cluster here, those are the patches along the diagonal line. Since they are spatial closer, they also show similar attention pattern. And this is also true for the Morton order or the spatial order. So now if I click individual patch, you can see on the very right, so all the patches in this block, stage 1, block 0, will always attend to the patches before the current one. But the word before, again, is defined according to our patch scanning order. If this scanning order is diagonal line, then all the before means the patches before the current one following the diagonal order. But if this order is this Morton order, then the before will mean those ones. That means before, because we have this patch order defined earlier. Okay, in short, we conclude the 3 things in this short paper. The first one is the attention pattern across different Mamba blocks are very different, but due to time limitation, I didn't explain this in detail. You can check our paper for details. Second one is the spatially closer patches often show similar attention patterns. And lastly, the order of image patches significantly impact the attention pattern in Mamba models. Thank you for your listening, and I'm ready to take any questions. Thank you.
So I have a question. So the ordering and then those sort of patterns that you choose,
Yeah.
Is there a connection between this and the interpretability of the model itself?
Yeah, actually, we introduced those new orders originally because we think the very initial order, which we call cross-scan, does not maintain the spatial locality very well. If you see the first row, anyway, if you go here and directly jump to here, there's a spatial jump. So this will not maintain the spatial locality. And then we actually try some order, like we do this way and then back forth, just to maintain the spatial locality. We originally believe this will better maintain the spatial locality and increase the performance of Mamba. But it turns out we didn't increase the performance, but we show, some way of perturbing the attention patterns using different orders. So in the paper, we conclude something, but we didn't draw a strong conclusion regarding the performance. But from the interpretation-wise, we believe this will help us better understand the attention between those patches. Thank you.
So that's conclude our session. We're only 3 minutes over time. So thank you, everybody. All right, now it's break time. Get some cake.
Could the presenters from the online, who will be presenting online for the last session, please stand by. We'll start testing in 5 minutes or so. If you could announce your paper, the name of your paper, and just put it into the WebEx chat, and we'll come one at a time and make sure that your connection's working and the audio is okay. Testing, testing. Can we have the last, the presenters from online presenters, please announce yourself in the WebEx chat.
Taste, taste. Hey. Taste, taste, taste.
Feilu, yes, if you can share your screen.
Okay.
Can you go into presentation mode? And if you have any video or audio,
Hey,
Yes,
why
sir.
flight mode? Sorry. Okay.
Do you have any audio that you'd like to test?
No, I
Or
have no audio.
only animation, that's fine.
It seems it's okay.
Yeah, and your microphone's clear as well.
Okay.
Any other presenters now would like to test from the last session of the day? Lichi Chen?
Yeah, can I test now?
Yes, please. Share your screen.
Okay.
And does your PowerPoint slide have any audio?
No audio. I
Okay,
think it's okay.
great. Yeah, so yeah, your microphone's clear as well. Thank you.
Yeah, thank you.
Okay, so Shaolin, are you there?
Oh, you hear me?
So can you turn on your presentation?
Okay. Is it okay?
All right. So your voice is clear, so you are good to go. So
I try to do some test.
yeah.
Or it will be okay.
Do you have any sound in the presentation?
There is no sound.
Okay.
Thank
Thank
you.
you. All right, so hello everyone. Thank you for coming to today's last session, applications. And I'm Jamin. I'm very happy to chair this session. And today we have 8 presentations, including 4 TVCG papers, 3 conference track papers, and 1 visualization note. And our first speaker is Fei Lu from Hunan University. And the title is Human-Guided Image Generation for Expanding Small-Scale Training Image Datasets. And this would be remote. Fei, please go ahead.
Hello, can you hear me?
Yeah, we can hear you.
Okay. Okay. Hello everyone, I'm Fei Lu from Hunan University. Today, I'd like to introduce our work, Human-Guided Image Generation for Expanding Small-Scale Training Image Datasets. The performance of computer vision models in certain real-world applications is limited by the small number of available images. Expanding datasets using pre-trained generated models is an effective way to address this limitation. However, since the automatic generation process is uncontrollable, the generated images are usually limited in diversity, and some of them are undesigned. To improve the quality of the generated images, there are 2 challenges. First, the number of generated images is usually large. Manually examining them is time-consuming. Second, since the natural language is complex, it is difficult for users to refine the prompts. In the literature, many methods have been proposed for interactive data generation. However, as they are not tailored to enhancing data expansion, they cannot be extended to improve the model performance trained on the expanded data. To track these 2 challenges, we first propose a multimodal projection method to help explore the generated images. We also developed a sample-level prompt refinement method to enhance the prompt refinement process. Based on that, we developed a data crafter to help enhance data expansion. This is an overview of data crafter. Given the original images and a pre-trained generated model and generate new images, then using the multimodal projection method to project both the images and content labels in a 2D plan for exploration. During exploration, users can identify which images are undesired or lack of diversity. Then refine the prompts through a sample-level prompt refinement method. The refined prompts be used in the next iteration. Next, we conduct a case study on past datasets. As the number of original images is small, the accuracy is low. Data crafter can improve it by 4.5%. When generating more images with data crafter, the accuracy can be improved by around 6%. Next, we focus on the first 2 steps in the case study. Our system consists of 5 views. An information panel to show the numbers of original and generated images and content labels. A metric visualization to show important metrics of the generated images. A multimodal distribution visualization to show images in the context of content labels. A prompt visualization to show prompt templates. And a detail panel to show selected images. Immediately generate 200 images for each class and explore them in a multimodal distribution visualization. In the visualization, the images are represented as circles. Their colors encode classes. The content labels are placed near the images. The pie chart shows the percentage of original and generated images that contain this label. Its size is the number of images that contain this label. Check the labels, find that the images in the upper part. Check Check the labels, find that the images in the upper part are many cats, and the images in the lower part are many dogs. Identify some abnormal labels that the light gray sector occupy much more than 2/3. To find much more such labels, we rank them in the information panel. The label tiger is ranked first, with the light gray sector occupying the pie chart. Select tiger and check the images. Let's move to the first step. Almost all tigers belong to the class Bengal. The detail panel displays the selected images and their original images. The objects in these images have the body of cats, but the face of tigers. Their associated prompt template is correct without any tiger-related description. Delete these images and a new prompt template is recommended. The images generated by this new prompt template are correct text. Check the new prompt template and find the name of the class is changed from Bengal to Bengal cats. Bengal is the name of an area in Asia instead of a breed of cat. One of the most famous breeds in this area is the Bengal tiger. Because the previous prompt template does not refer to the Bengal cat, the model might wrongly interpret it as Bengal tigers. The expert feels the new prompt template is correct and accepts it. Let's move to the next step. After generating with the new prompt template, the informativeness metric increases and the distance metric decreases, which meets his expectations. However, the diversity metric decreases, which might limit the model's performance. Check the newly generated images of class Bengal and find new label garden and flower arise in this area. The new prompt template contains in a starting garden, which limits the scene of the generated images, thus decreasing the diversity. He selects these generated images and add more images. Then, a new prompt template is recommended. The scene description in the new prompt template become more defined. After that, the diversity metric increases. Moreover, the generated images cover a larger area. Both of these patterns indicate an increase in diversity. The expert feels the new prompt template is correct and accepts it. After demonstrating the case study, I want to explain the technical details. First, I will introduce the multimodal projection. The multimodal projection places the image and their content labels on a 2D plane. There are two projection goals. First, similar images and content labels should be placed together. Second, images should be paired with their corresponding content labels. Based on an image that contains how many labels, we categorize it as a many-to-one setting and a many-to-many setting. A recent work, Model Fusion Map, uses an order loss to solve this problem. However, in many-to-many setting, it doesn't work well. To figure out why, we conduct a theoretical analysis. In many-to-one setting, we prove that the distance orders between image and the content labels can be exactly preserved. And in many-to-many setting, we prove that the distance orders can be exactly preserved only when an image contains no more than 3 labels. So, to solve this problem, we choose the contrastive learning, which has been theoretically proved can be an approximate stationary solution. In this method, we use the 3 types of contrastive law. For images and content labels themselves, we use the nearly same labels to construct the positive and the negative pairs. For an image with the content labels, we construct the pairs based on whether the image contains the content labels. We conduct both quantitative and qualitative experiments. For quantitative comparison, our method performs better than the multimodal method. And for projection quality, our method can clearly separate and preserve both the intra-modal and intermodal relationships. Next, I will introduce a sample level problem refinement method. The key change is how to guide the generation process. A straightforward solution is directly modifying the prompts, but it's too complex for users. We use an evolutionary algorithm-based strategy to automatically modify the prompts only needed to see the images. According to the
2 minutes
set
left.
theory, we have identified two types of operations for users, add and delete, and we designed two objectives for them. To conclude our work, we present data crafter to enhance automatic image generation for data expansion in computer vision tasks. In the future, there are several directions, like operations on multiple sets, and they extend to other types of images. Thanks for your attention. Our paper and code are online available. I'm happy to take questions.
All right, thank you for the presentation. Any questions from the audience? So I have a question for you. So when the user, for better diversity, the user can change the prompt templates, and when they change the templates, is there a certain support for them, or they need to manually change the prompt templates?
Right. Pardon? I cannot hear exactly.
Okay, so
Can you repeat one?
you mentioned the evolutionary algorithm, right, for the prompt refinement. Can you hear me?
No, the sound thing is more. I can.
So how is the recommendation for prompt templates generated?
Okay, I know. We use the GPT-4 to
Huh?
automatically modify the prompts. To be specific, we use the modified prompts to generate several images and evaluate them with the objectives. If it is better, we will select this prompt and go to the next step. If worse, we will use the previous prompt. In our setting, we set the steps. The number of steps is 5 to reduce the time.
So, okay, thank you for the answer. And let's thank the speaker one more time.
Thank you.
And the next speaker is Xiaolin Wen from Nanyang Technological University. And the talk is pretty smart, visual interpretation of smart contracts via simulation.
Hear me?
Yes, we can hear you.
Okay. Hi, everyone. My name is Wen Xiaolin from Nanyang Technological University, and I'm very glad to be here to share our paper, Pretty Smart. And this paper is a joint study by Nanyang Technological University, Singapore Management University, and GoPlus Security. And in this study, we propose a system called Pretty Smart to offering a visual interpretation of smart contract via simulation. And before we talk about smart contract, let's look at what is traditional contract. For traditional, the sellers and buyers will come together and sign a contract, and they will rely on third parties to supervise the execution of the contract. But it's a little bit slow and complicated. Now we have smart contract. Smart contract is programs run on the blockchain, and it can be run on blockchain automatically when some conditions are met. So it can efficiently remove the need for third parties. Because it's automatic, so it's more efficient and accuracy. And no one can change it because it's deployed on the blockchain, so it's kind of secure. And all the source code of smart contract are publicly available on the blockchain, so you can rely on it. But why do we need to visually interpret it? Let's see an example. If someone said they have a smart contract for investment, and you can invest money and they will give you profit. They say it's the highest profit, zero risk, and scam impossible. That's because the source code is available on the blockchain, and everyone you can check and to see how the smart contract works. Will you invest in your money? I think if you are novice investors, you will feel a little bit confused because the source code of the smart contract is a little bit complex for you to understand. And someone will ask, why not use existing transaction patterns to analyze how smart contracts work? If the smart contract is a new one, there could not be enough existing transactions for you to analyze this. And before we go through the visual interpretation, we first see how the smart contract worked on the blockchain. This is an example for the source code of smart contract. Like normal program, it includes state variables to store some necessary information, and it also have some functions to control its execution. Take the Ethereum blockchain as an example. The smart contract code will be deployed on the Ethereum virtual machine, and the user can use the functions API to call these functions and to interact with the smart contract. And all these interactions can be recorded as a transaction on the blockchain. Typically, the users can use different function calls to do some behaviors like money transfer to the smart contract. And the smart contract will be run on the blockchain and change some state variables. And maybe they will send some money to others via internal transactions. And finally, the related user's balance will be changed. That's how the smart contract works. And next, what we do in this study, we propose a visual analytics system called Pretty Smart. Our rough idea is here. We first use a simulator to simulate multiple users and owners of the smart contract. And then we generate the possible function calls of each user. And we use a local virtual machine to run these possible function calls and construct the cryptocurrency flows. And based on this cryptocurrency flow, we compute the net balance changes over time. And the investor can, based on this information, they can understand how the smart contract works and how each function works. And further, we propose a state variable changes for some users with the technical background. They can understand the state variable and they can use this information to further confirm their analysis results. Overall, with this visual interpretation, the user can, based on this smart currency flows and balance changes and function calls, to understand the smart contract. And next, let's talk about how we collect data for the visual interpretation. We propose a simulator. This simulator take the smart contract source code as the input and to use a fuzzing tools to generate the possible function calls. And then we rerun these function calls via virtual machine and to collect all those information during the simulation. So after get the data, this is the interface of Pretty Smart. And I will introduce the visual design one by one. The first one, we have a simulation overview. It provides a visual summary for each simulation, involving the net balance over time and invoked functions. Specifically, the y-axis lists all the simulated users and also the smart contract. And the x-axis shows the timeline, the function call sequence. And we use the color of the rectangles to encode the net balance. The blue means the positive number, means they win money, and the red means they lose money. And we also use the circles to encode how many functions involved in this simulation. And after you click one simulation, you can see the detail of this simulation. We have a function summary to show the statistic of the cost of each function in a simulation. And you can see the triangles to identify whether this function can be used to do money transfers from the caller to contract, from contract to caller, or from contract to others. And the right bar charts show the statistic information of different function call type. And function call detail is the main view of Pretty Smart. It demonstrates the detailed behaviors of the smart contract after each function call. Layout is similar. The y-axis lists the contract as all the simulated user, and the x-axis is the timeline. And we have 3 layers in this design. First layer is the function call. This layer shows which user call what functions and at what time. You can see this by the position of the rectangle. And the second layer will show the money flows, use the red and blue curves. The red curves means the user send money to the contract, and the blue curve means the contract send money to some users. And the width of the curves encode the concrete value of the money transfer. And the third layer is the net balance. Here we use an error chart to show the net balance change of each user. You can see the blue one is the positive net balance, and the negative net balance is encoded by the red. And as I mentioned before, we also provide state variable changes to show how the state variables are changing after each function call. And here we list all semantic meaningful variables here and use different symbols to encode different variable type. And we also highlight the changing pattern of the variable, like the increase, decrease, or not change. For evaluation, we conducted 2 case studies to demonstrate the effectiveness. And next, due to the time limit, I will introduce the first case to demonstrate how to use Pretty Smart to interpret a gambling contract. First, we can see for this contract, we generate 7 simulations. And when we check the balance change of the smart contract, we can see the blue going dark and abruptly be white. So it means the smart contract net balance is going up and abruptly decrease to 0. It means because this smart contract can collecting money first and then send all the money out. And after that, we can see the simulated users net balance changes. We can see every user have both red color and blue color. That means everyone have the opportunity to win money or lose money. So for a gambling contract, it's kind of fair. And after you click one of the simulation, you can see the detail of this simulation. In this simulation, we can see this simulation involves 2 functions: the function 0 enter and function 1 pick winner. And we can hovering on these function summaries to show the detailed behaviors of this function. While we're hovering on the F0, we can see everyone can call this function. And after call this function, there will be a red curve from the caller to the smart contract. That means this function can be used to send money to the contract. And after this function call, the contract's balance will be increased. And after you're hovering on the pick winner, we can see only the first user can call this function, and the first user is the smart contract owner. That means this function can only be called by the contract owner. And we can also see the blue curve from smart contract to a user.
2 minutes
So
left.
this function, okay. So this means the owner can call this function to ask the smart contract to send money to someone. So let's see the function call detail again. There are some repetitive patterns, like someone called the first function to send money to the contract first, and then after a while, the owner can call the function 1 to pick a winner and to get all of the money. So that's how the gambling contract works. After that, we have a user interview with 12 cryptocurrency investors to evaluate the Pretty Smart. And the result shows Pretty Smart is effective and useful for investors to analyze the smart contracts functionality. So finally, we have some takeaway message. Although the source code of smart contract is publicly available on the blockchain, but not everyone can understand it. So smart contract simulation is more easy to understand than the source code for the investor. And the second one is visual interpretation of smart contract is an intuitive way to inform investors of how a smart contract works. Okay, thanks for your attention. That's all my presentation. For more detail, please check our paper. And by the way, we have a serious works about the smart contract visualization. If you are interested, you can check it. That's all. Thank you.
Thank you. So any questions from the audience? So I have one. So I'm curious about the scalability of your system. So how many, for example, users or addresses can your system handle in the simulation?
Oh, okay. For the simulated user, its parameter can be set by the system user. You can set whatever how many users you want to simulate. But for the visualization, I think if there are too many users, there will be some scalability issue. You can use some zoom in, zoom out, or scroll bar to deal with this problem. But I think during my study, usually maybe 5 or less than 10 users is enough to understand the simple smart contract. So I think it's kind of okay.
Okay. Any other question? So I have another for you. So how did you ensure that every part of the smart contract code is executed in the simulation?
Okay. We use existing smart contract parsing tools. This kind of tools, the purpose of this parsing tools is to explore all the branch of the code. So after the simulation, maybe it can ensure the comprehensiveness of our simulation.
All right. So let's thank the speaker again.
Thank you.
And the next speaker is Yue Yu from the Hong Kong University of Science and Technology. And his talk is about InclusiVis, visual analytics of human mobility data for understanding and mitigating urban segregation.
Okay, thanks for the introduction. Good afternoon. My name is Yue, and you can call me Bruce. Today, I'm excited to present InclusiVis, a visual analytics system to understand and help mitigate urban segregation using human mobility data. This work was a collaboration between HKUST, Northwestern University, Stony Brook University, and UC Davis. Urban segregation is a severe problem that divides cities, separating people based on wealth, race, or beliefs. Why does this matter? Social scientists discovered that cross-group interaction drives economic mobility. Mitigation of segregation can enhance social inclusivity and improve social well-being. In this paper, we aim to design a visual analytics system to help social scientists understand the segregation patterns and use what-if tool to explore strategies to mitigate segregation. This brings us to several key challenges. First, how can we analyze fine-grained segregation patterns effectively? Second, how do we understand the complex relationships between places and mobility? Third, how do we bridge analysis insights into actionable interventions? Recent studies use GPS data to measure segregation in daily activity spaces by calculating indices for different places. This provides insights into how different groups interact or fail to interact. However, they often miss the local detailed patterns. They also lack tools to help policymakers to evaluate interventions effectively. This is where visual analytics can help bridge the gap. The visualization community has developed many techniques for mobility data like flow maps or matrix views, often enriching them with context like points of interest or social media text. These help reveal complex mobility patterns. But most don't integrate demographic data, which is crucial for understanding segregation dynamics for social scientists. What-if analysis tools can also allow urban planners to simulate changes in urban scenarios such as land use and epidemic control. However, existing tools may not focus on inclusivity or use regression models that oversimplify complex mobility drivers. We propose solutions to tackle the challenges mentioned before. To handle the fine-grained analysis, we propose a three-level workflow. We start with the community level, which is a large district in the city. Then we drill down to the census block group or CBG level, like a small neighborhood with a few residents, with a few hundred residents. Finally, we enable intervention design and the specific points of interest, like shops or parks. To understand complex environmental correlations, we adapted a state-of-the-art human mobility prediction model called deep gravity. For each social group, like high income or low income, we trained a separate model to predict their mobility flow between the origin and destination based on features like population, POI densities, visitor characteristics, and distance. We then use shape value, an explainable AI technique, to help understand why the model makes such decisions, showing each feature's influence. Finally, to bridge insights and action, we built InclusiveVis, which allows interactive analysis and experimentation with planning interventions, showing predicted impacts instantly. Throughout the design, we collaborated with the domain expert experienced in segregation analysis. This led to 5 key design requirements under 3 levels of analysis. And we designed a system with 4 main views to support these requirements. The community view offers a city overview, segmenting communities and comparing their social demographics. The CBG view ranks CBGs to find the targets with intervention potential. The map and what-if views analyze visitor flows and feature impacts. The what-if view simulates POI changes with real-time feedback. Let's look closer. In the community view, users can select a city or an attribute of interest like income. For the mobility dataset, we can construct a mobility graph for the city, with each CBG as a node and the number of people traveling them between them as age weights. And we use latent algorithm on the graph to detect communities. To compare communities, we designed the community signature. It's originally from a box plot showing the distribution of social groups for the CBGs within that community. But now we only focus on the interquartile range to quickly understand the primary characteristics. For example, we can quickly find that community A in green has a very diverse distribution across different social groups, while community B has a very severe concentration on the first column, which is the low-income population. The flow matrix below visualizes intercommunity mobility as an adjacency matrix. Each cell shows the flow between 2 communities, with bars representing the social groups of visitors and the background color encoding the flow volume. For example, the light background shading of this cell indicates minimal visits from community A to B, even though they are very close on the map. Moving to the CBG view, the ranking table lists CBGs within a selected community. We calculate 2 indices, the segregation index measuring visitor diversity at the CBG, and the bridging index estimating potential diversity from nearby residents. Following prior work and expert suggestion, we want to find CBGs with high bridging index, but still very high segregation. We use TOPSIS, a dual attribute ranking method, to prioritize these CBGs. The map view provides geographic context with the navigational map and a dolly map, which preserves the geographic relationships between CBG. It visualizes detailed visitor flows between the target CBG, filled in black, and its closest neighbors. In the dolly map, each CBG is represented by our filter bubble glyph. The shape of the current CBG is at the center, and the glyph area shows the population size. The arcs inside shows the resident demographics of that CBG. If one group dominates, it looks like an isolated bubble, visually hinting at the segregation. The thicker outer arc shows the proportion of the residents from this CBG visiting the target CBG. So on this dolly map, we can learn that this CBG in community A, in green near the target CBG, is economically diverse, but contributes very few visitors because it has a very short outer arc. In contrast, this one in community B is segregated with the majority of low-income residents, and it has a lot more visitors to the target CBG. So if we can attract more visitors from this CBG to the target CBG, we can reduce the segregation to some extent. Let's move to the what-if view to find out how to open the black box of the deep learning model to help us understand influential features. The CPC score at the top indicates the model's prediction accuracy for the target CBG. The feature control panel shows distributions for POI features across the city. The vertical lines indicate the target CBG's current value. On the right are feature impact plots, one for each social group. Dots show the average shape value for each feature, which is its average impact on attracting or repelling that group. At the top, the bars show the visitor proportions from different social groups. For example, we can find that the medical POI has a more significant negative impact on median-level income groups, which can be a major reason that the target CBG distracts these people. Hovering on a bubble glyph of a specific origin CBG arc shows instance-level shape values as a line. To evaluate the effectiveness of our model adaptations, we compare our model against different model settings in two cities datasets using 5 metrics, and we found that our model setting outperforms others. We then evaluated inclusive weights through 2 case studies with 4 domain experts from different fields. Let me show you one case about income segregation. In the community view, the expert first compares income signatures. He quickly identifies community B as distinctly low income and isolated, noting its minimal interaction between the diverse adjacent community A inflow matrix. Wondering how to bridge this divide, the expert focuses on community B. Using the CBG view, the expert selects the top-ranked CBG with the highest intervention potential. It will trigger updates across the system. The expert then investigates why this CBG is segregated. On the dolly map, filter bubble glyphs show that the target CBG is mainly visited by low-income residents, with very few visitors from nearby affluent areas. To understand influential factors, he turned to the what-if views feature impact plots. Sorting by shape value variance, he discovered that the density of health-related POI is a key differentiator, and its absence strongly deters middle-income groups. Based on these insights, the expert decides to test the intervention. Using the feature control panel, he simulates increasing health-related POI density in the target CBG. He got immediate feedback. The ranking table predicts a drop in the segregation index. The dolly map visualizes increased flows from the diverse community A using the gold arcs. Hovering on one CBG confirms that the intervention positively impacts middle-income visitor attraction. In conclusion, inclusive weights makes 3 main contributions. First, we characterize the problem domain. Second, we define a comprehensive segregation analysis workflow with a deep learning model. Third, we created a visual analytics system with novel designs to understand and mitigate segregation. The future works may incorporate temporal dimension into mobility analysis, improving the precision of visitor demographic data to include some individual level GPS data and enhance both computational and visual scalability using techniques like progressive visualization. Thank you for the attention. I'm open to discussion and collaboration. I will soon graduate from my master degree, and I'm generally interested in computational social science and human AI collaboration. You can check out more of my other works on my homepage, and I'm happy to take questions. Thank you.
So any questions from the audience? So I have one. In the case study, I found out that there were 8 communities identified by the algorithm. Was it common, or the number can change?
Yes, we have set a maximum number of the community, which is 10. So if the community number exceeds 10, we will summarize the other remaining small communities into one other community. But if the number of community is less than 10, then the community number is flexible.
Okay. The other question? All right, so thank you for the talk.
Thank you.
And our next speaker is Yi Han from National Sun Yat-sen University, Intivisor, a visual and analytic system for interaction log analysis.
Okay. Good afternoon, everyone. My name is Yihan, and today I'm happy to introduce my work, Intivisor, a visual analytics system for interaction log analysis. My co-authors are Gregory About and John Stasko. So imagine someone develop an application and put it online. Take PacificVis, for example. Maybe some of you know this. It visualizes IEEE Visualize InfoVis publications. And it may have some interactions, such as supporting, well, finding some interactive citation patterns over here. Every circle is a publication. It also has some drop-down boxes. It has some search boxes, so and so on. Now, this information, a developer may want to know, hey, well, are there any design issues with the system? Does it support the user task we designed the system to support for? And are there any unexpected use cases, for example? Now, this information is invaluable for improving the application design. Now, one way to get this information is through analyzing interaction logs, basically what people are doing in the system. And it can be easily collected at scale. And a log or PacificVis may look something like this. Has some timestamps, has some details, but it is still very messy and complex. So typically, for analysts to analyze this data, what they do is that they use an interaction analysis approach. And using this approach, they start from inspecting the log, understanding basically what are logged, and maybe form some analysis goals. How am I going to go about analyzing this data? Now, after they inspect the data, typically they get into an event organization stage, where they start from selecting events that may be relevant to their analysis, which includes maybe things that they care about. Maybe they may also look into, well, is the log event in the right granularity? Because sometimes some events occur together a lot, put them together. Some may not have enough details, split them out, so and so on. And that is for basically filtering out irrelevant events, because they can introduce noise into the analysis. And to obtain the right granularity for the analysis you have in mind. Now, going forward, the next step is typically a categorization process. It is an abstraction process. Sometimes some events, they may be actually doing the same thing, such as clearing the selection or something like that. You might want to categorize them further. to basically, well, further reduce the complexity in the data and create a new unit of analysis that better meets your analysis needs. Now, after the event organization stage, now we get into the pattern discovery stage. And typically, analysts conduct some kind of sequential pattern analysis to automatically extract frequent sequences in the data, because these interaction sequences may inform high-level user activities that can be very useful to understand behaviors. Finally, all these sequences and categories, they need to be put back into their original usage sessions to understand basically the context of these interactions, to better understand things. So this is the entire process, and typically in a real analysis, this process is iterative, because maybe when we're looking into data, we have some new ideas, we need to go back to reorganize data, and then the process starts again. So this is actually very important for practical analysis. But in some existing work, we notice that many visualizations really supports the pattern discovery phase very well, but not so much in the event organization. It's not like they don't do it, it's just that they do it sometimes or oftentimes outside of the system. For example, the categories may be predefined in some way outside of the system. And we think that really limits the flexibility in this event organization process and the overall effectiveness of the system. So we developed InterVisor, a visual analytics system for interaction log analysis that basically covers this entire end-to-end process with 5 perspectives that maps to each of these stages that I mentioned. So what is it? Let's have a look. So I'm going to put that over there. The stage looks like this. The first inspect stage, we have a basic visualization that includes sessions, kind of listed over here. And then when you go into the session, you can see the interactions over time. Now, from an analysis point of view, it's very important to kind of first go through the data, maybe session by session a little bit, to understand what's actually logged, to know what is useful for their analysis going forward. Now you have a general understanding of the log, you get into the select stage for event organization. Here we have 4 columns over here. The first column basically is for storing the selected events that's relevant to the analysis. And the 3 columns over here are the unselected events. These are the individual events. These are pairs of events that probably go together a lot. And these are triples of events. And they are ordered by frequency because we kind of thought that it's very common for developers to look at frequent behaviors inside the system. So things that go together may represent that. So they may want to select them all together into a unit for further analysis. So a selection process may look like this. They start selecting events over, and this list becomes shorter and shorter as the list is being kind of moved over. And there's also one little process over here. We can also split events, but because it's a little complex, I'm going to leave it out in the talk over here. Now, once you have the events selected, they will be listed to the left-hand side over here in the categorized perspective. Now, the categorized perspective comes with a canvas, and this canvas is basically blank in the beginning, and its purpose is like a whiteboard where people can organize things on it, just like when you use sticky notes to organize ideas, right? Now, this open canvas provides a space for basically the analysts to come in and kind of create their own organization scheme, however they would like it. So to help with this process, we actually also provided some sketching tools where they can just create some kind of background over here, maybe add some labels, some boxes that represent the visual elements, and then they can start categorizing things based on this scheme. So how it works looks something like this. So for example, if we want to create a little scheme, maybe maps a little bit like our user interface, and we can just kind of put some of these labels over there. Now, when I see this, I know, okay, this is where this interaction means, this is where that one means. This is just one way to categorize it. Now, the categorization process goes from, well, selecting these events and dragging them over to the organization space. So For example, we may be dragging one event to one category. That is possible. But if you want to rename the categories, events into the same category, you can just drag it on top of each other and they will form a new category. Okay. Now, after the categories are formed, now we get into the sequence stage. And this sequence stage automatically uses an algorithm that extracts frequent sequences inside the events in the categories. And over here, you can see that we have little edges in between to indicate some sequence that's being automatically extracted. If you like, you can change some parameters and we can extract different sequences for you as well. Now, once the sequences are extracted, now we get into the final stage of our analysis, which is let's put everything together. Now, the sequence in the canvas is on the upper left-hand corner. Now, it's like creating a little bit of this is where everything is organized. And on the right-hand side are the original usage sessions. And you can see that we actually colored these categories over here and mapped the colors over to the sessions. So now you know where these categories occur in their original usage sessions. Okay? Now, the sessions basically look something like this. Every bar is a session, and you can see the colored categories. And we also, by default, sorted them by length. Okay, this is just one way of sorting it. Now, here's the thing. You might not just want to look at this in its original way, so you might want to do some queries, which is very typical in analysis. So to query an interaction, so for example, to look for a specific interaction, where did it show up in the log, we can actually use an interaction in this canvas, selecting a color, which may not need to be the original one we automatically assigned, and it will show up over here on the right-hand side where they show up in the original sequence. The pattern will be shown up here, and that provides you an understanding of maybe some sessions have more of them, some have less, how things are doing. Now, if you don't like to sort them by length, which may not always be the way you want to analyze and want to look at it in different ways, you can, for example, sort it by time. Now you can see if there are any temporal factors in using these sessions, because sometimes people introduce new features. Time can be a very important factor in the analysis. Now there are more ways to query. You can look for more categories and they would just kind of be put side by side and all be highlighted. You can look into categories that has a specific order. So for example, this one needs to occur before that. So we can use this maintain order button and 3 dots will show up to indicate only when they occur in this order will they be highlighted and shown over here. If you want, you can click on the 3 dots and they will merge together, saying that these 2 categories needs to occur back to back. Okay, that's a different way. We don't have an example over here because the query shows up empty. But if you want to query the frequent sequences we were talking about, you can kind of click on the lines over here, specify colors, and they will be showing up over here as well. So different ways to query data inside their original sequences. Now, to understand how this works, we kind of conduct how well it works. We looked into an evaluation with 4 applications. The developers log their own data and analyze it themselves as well. So just a brief overview of our findings is that overall people do find it very promising and flexible, and they are able to use our tools to organize their events. And we do find that most of the interesting patterns they found were found with low effort. That's basically based on a questionnaire they filled. However, there is a concern is that the categorization process, when it involves sketching and drag and drop, can be a little laborious. So that part can be improved. Now, the conclusion is that we developed a visual analytics system called Intervisor that supports both event organization and pattern discovery. Even though the event organization can add some work to make it a little less laborious, it does show to be very useful. So future work to try to address that, to make that easier. Thank you.
Any questions? Yeah, please use the microphone.
Thank you very much for a great talk. And well, actually, I thought that categorization is a labor-some, and I want to ask, can we reuse the result of categorization in all other stages work for different kinds of query? Do you have any experience about that? So if I put some hard work doing that multi-stage stuff, then I want to reuse that result over and over for different types of queries. Is it possible to do in your experiment?
Let me see if I understand you correctly. Do you mean that now we have an organization of these categories? Can we take it out and reuse it in other work? Is that what you're saying?
No, that's for the same data set
Or
and
the
for a
sa-
different purpose, different analysis purpose.
I think we do have a save function. Actually, I don't think I actually mentioned that too much. You can actually just do something to a stage and you can save it. So if you want to kind of come back to a previously categorized things, I think that is possible.
Then, as you mentioned, can you use that categorization station for other work?
Do you mean exporting it for another work? It's saved in a specific format. If you have another system that can parse it, I think it's possible.
Okay, thank you very much.
Okay.
So one more question from the audience. So I have one. So how do you extract some higher level meanings from the low level interaction logs? For example, a click event can mean different things. For example, if it happens on an empty space, it may mean some clear selection, but while on an item, it can mean the bigger selection. So how do you distinguish those two events?
I think that's a hard question for an analyst. And that is why in our study and in our work, we assume that the person, well, actually not we assume, we actually have the person who developed the system to analyze it so they know exactly what every feature works. So that actually helps a little bit. But if there's some novel use, maybe there's something that they need to kind of look into. Because yes, interaction analysis, sometimes there's a lot of context. There's a lot of information. Log analysis, there's one thing, it doesn't log the entire screen. It's not like a screen recording. So sometimes you don't know what exactly they saw. Sometimes, in fact, in our study, we found that sometimes when people forget to log certain important things like system messages or something like that, in the log analysis, they run into a problem. So it's important to make this process iterative and learn and analyze it and do something like that.
All right, so let's thank the speaker again.
Thank you.
And the next speaker is Jiwon Choi from Sungkyunkwan University, Waltz board, multi-criteria automated dashboard design for exploratory analysis.
Hello everyone, my name is Jiwon from Sungkyunkwan University, and today I'm presenting Wellsport, an automated dashboard design system for exploratory analysis. This work has been done with my advisor Jaemin. Dashboards are highly versatile visualization tools employed across numerous domains, including business intelligence, public health monitoring, and even in highly technical domains such as machine learning evaluation. They provide readers a glanceable overview of complex data, facilitating rapid comprehension. However, although dashboard readers benefit from this nature, dashboard authors often need to utilize complex tools or codings to create these visualizations, which is time-consuming. This significant effort naturally leads to considering automation as a potential solution, yet designing effective dashboards automatically presents significant challenges. First, there is no golden rule for dashboard design. The effectiveness of dashboard is highly dependent upon the specific analytical task and users' evolving needs. Furthermore, the potential design space is combinatorially large. Previous automated systems have sought to address this complexity, like machine learning-based approach can learn design patterns of the dashboards, but typically necessitates the training data sets and lengthy training times, limiting their utility for rapid exploration. Template-based systems offer speed, but exhibit limited flexibility due to their reliance on a fixed number of templates, particularly when user's intent is varying in exploratory analysis. To overcome these limitations, we introduced Wellsport, an automated dashboard design system developed for exploratory data analysis. Wallsport is designed with three primary objectives: flexibility, speed, and interpretability. The user interfaces comprises three main components: the intent panel on the left, allowing user to articulate their analytical needs; the central dashboard panel, which displays the automatically generated dashboard; and the reasoning panel on the right, providing transparency into the underlying design process. A core feature of Wallsport is its flexible mechanism for expressing user intent. Rather than selecting from predefined analytic goals, users employ their weight controller to adjust the relative importance of 5 key effectiveness measures. Additionally, the token controller enables users to specify preferences or exclude specific chart types, attributes, and data transformations. After expressing intents, user receives a dashboard instantly, typically within seconds, enabling immediate data exploration. Wallsport incorporates features to enhance interpretability. The reasoning panel provides dashboard-level understanding by comparing current dashboards to current candidate and score distribution view, and showing the estimated sampling probability of each chart components in the token probability list. Chart-level reasoning is supported by the detail panel, which shows the score ablation result of each chart and the statistical features. To implement this dashboard design workflows, we first need to know which dashboard is effective. However, as mentioned before, effectiveness of dashboard is context and text dependent. Instead of building single criteria of effectiveness, we take the bottom-up approach. Based on previous studies, we first identified 5 dashboard effectiveness measures for exploratory data analysis and multi-view visualizations. The first is specificity. This asks the question, how well does a dashboard fulfills the user's specified preferences? For example, if a user explicitly specifies interest in sales or profits attributes using our intent panel, a dashboard featuring charts about these attributes would score higher on specificity. The second dimension is interestingness. The core question here is a dashboard statistically interesting? Inspired by previous systems, this measure looks for statistically significant patterns within the data visualized in the chart, such as high correlation, skewness, or presence of outliers. A dashboard revealing such patterns is considered more interesting. Third, we consider diversity. This addresses how distinct are the charts from each other. Research on multi-view visualization and systems suggests that showing data from various perspectives using different chart types, attributes, or transformations facilitates broader explorations. Our diversity metric quantifies this variety within the dashboard. Fourth is coverage, which asks how many attributes does a dashboard cover? Especially in the initial stages of exploratory data analysis, users often want a broader overview of the data set. This measure tracks the proportion of data set attributes represented in the dashboard. Finally, we have parsimony. The question is simple: is a dashboard concise? Parsimony favors dashboard with fewer charts, ensuring glanceability and reducing complexity. Then we formalize these 5 aspects into simple quantifiable metrics. Please refer our paper to get details of each equations. The overall score for dashboard D is calculated as a weighted sum of the 5 individual measures. The weights are directly controlled by the user with the weight controller in the intent panel, allowing the system to tailor the optimization objectives to their current analytical needs. With these measures and scores, we can formulate the problem. We represent dashboard D as a set of charts, each chart abstracted as 7 tuples of chart tokens, capturing its chart type, encodings, and any transformation applied. The goal then becomes finding the optimal dashboard, the best, which maximizes an overall score function based on our effectiveness measures. Finding this optimal dashboard requires navigating the huge search space efficiently. Our automated design process consists of 3 phases. The first iterative sampling phase randomly design dashboards by sampling chart tokens from probability distribution. These random samples are scored by scoring function with user intent. Then top performing dashboards are selected and their token counts update the distribution to learn effective chart designs. In search phase, we use learn distribution to build a promising candidate chart called chart vocabulary. We then employ a beam search guided by our score function to find the high scoring dashboard in a few seconds. Last phase is refinement phase. In this phase, the user interacts with the generated dashboard, replacing chart with system suggested alternatives, or adding new recommended charts, allowing fine-tuning based on their evolving insights. We benchmark Wellsport performance using our 4 diverse data sets. Our evaluation compared configurations that mirror the stages of our automated design process: a random baseline, iterative sampling stage only, iterative sampling and search phase, and the full 3-stage algorithm, including simulated refinement. We measured both the overall effectiveness score, assigning uniform weight to our 5 measures, and the total computation time for each configuration. Results demonstrate that each phase in algorithm proceeds, the score generally increases, with the full algorithm producing dashboard scoring is 37% higher in effectiveness rather than random baselines. The complete 3-stage process finished in under around 5 seconds for most datasets, enabling interactive exploration, which confirms that Wellsport's multi-stage automation effectively balances speed and quality in dashboard generation. To qualitatively evaluate Wellsport, we conduct a user study with 8 participants experienced in visualization tools. Our goal was to assess its effectiveness in facilitating exploratory data analysis and satisfying user intent. The study involved 2 tasks: a focused analysis task requiring a dashboard about profitable movies, and an open-ended task encouraging free exploration of student performance dataset. Our results highlight 3 key aspects. First, regarding intent expression, we found that Wellsport accommodates the diverse analytic needs users bring to exploratory analysis. Second one is Wellsport facilitates data exploration. Its capability for instant dashboard generation and refinement help users to quickly start their analysis and provides guidance throughout the exploration process. Third, interpretability features can help build trust. The component designed for interpretability assists users to trust the automated suggestions. However, we observed that while helpful, these features can sometimes impose cognitive load because of the extra visual components. In conclusion, we first defined the framework to quantify dashboard effectiveness based on 5 aspects derived from prior studies. Then we designed and implemented Wellsport, an automated system that instantly generates dashboard reflecting user intent without requiring pre-computation or training data. Our evaluations show that Wellsport can effectively facilitate the dashboard design process and supports flexible data exploration for diverse analytic needs. Thank you for listening.
Okay, so questions from the audience? So please ask a question because I don't want to make a question about my own paper. No questions? All right, so if I have to. So I saw that you included a couple of chart types in the optimization process. Are they quite limited? Can you increase the number of different chart types?
Yeah. Our framework and algorithm is like kind of agnostic to chart types, so we can add new types of chart types and how can be rendered in the client. We code that and implement to the system, then we can add new chart types to our system.
Okay. No further question? All right, so let's thank the speaker again.
Thank you very much.
The next speaker is Midori Sugihara from University of Tsukuba. Contribution of data visualization to decision making, a classification of data visualization research based on the characteristics of decision problems.
Good afternoon, everyone. My name is Midori Sugihara from the University of Tsukuba in Japan. I'm PhD student and my supervisor is Kazuo Misue. He is here. Today, I'll present our research on how data visualization support decision making. We conducted a systematic review spanning 60 years and analyzed the characteristics of decision problems addressed by data visualization. Here's a quick overview of today's talk. I'll start with background and motivation and research questions and contributions and related work. Then, next, I explain our methodology, highlight key findings, and finally share our conclusion and finally directions. Data visualization is widely used in areas like business, healthcare, and policy making. But decision problems vary greatly in structure, scope, and importance, etc. To create effective visualization tools, we need to understand what type of decision problem data visualization support best, and where gaps remains. To address this, we applied a multidimensional framework and analyzed 40 empirical studies over the past 60 years. We aimed to answer 3 questions. 1, what type of decision problem has data visualization supported, and how has that changed over time? And if so, how? By addressing this question, we clarify the evolving role of visualization in decision making. While previous research highlights the value of data visualization, but few studies take a comprehensive multi-domain view. To fill this gap, we used Franz and Kramer's multidimensional decision-making framework to systematically classify the decision problem addressed by visualization. This diagram shows our research process. We collected paper and applied 2 levels of screening and used the framework to classify decision problem types. We collected 351 papers from 7 major venues like TVCG, PacificVis, and so on. After primary screening, 2-on-2 focused on human decisions. We then selected 40 empirical studies published from 2008 to 2024. And we used 10 dimension, 8 from Franz Kramer's. Franz Kramer framework has like scope, type, structure, etc. And plus 2 dimensions we added, applied context and user expertise. This allowed us to systematically classify each paper's decision problem. And finally, re-evaluate and classify each paper's. We don't have time today to go into full details of our screening and classification process. But if you're interested, we describe them in depth in the main paper and supplementary materials. This heat map provides an overview of the 40 empirical studies we analyzed, classified across the 10 decision-making dimension we introduced earlier. On the vertical axis, we list each dimension of decision-making problem. On the horizon axis, we list each dimension. On the horizon axis, we show the different characteristics within each dimension. Each cell contains a number, indicating how many papers address the decision problem with that specific characteristics. The darker the color, the higher the count. This comprehensive view helps us identify dominant patterns and sets the stage for the next few slides, where I'll highlight 3 key findings based on the heat map. Our first major findings reveals that data visualization primarily support organizational level decision making. As you can see in this slide, the majority of the 40 papers we reviewed focus on organizational context, with this trend remaining consistent over the 60 years period. In contrast, there is almost no support for family-level decisions, as highlighted by the red cycle, and minimal support for individual-level decisions. This pattern aligns with the evaluation of decision support system, which developed from executive tool in the 1970s into business intelligence platform with visual analytics by the 1990s. These systems address complex interconnected scenarios requiring collaboration, areas where visualization tools prove most valuable. The cross-analysis matrix at the bottom right, bottom right confirms this pattern. Organizational decisions are typically interconnected with other decisions, while individual decisions tend to be more independent and self-contained, requiring less sophisticated visualization support. Our second key findings is the evaluation of decision-making types supported by data visualization. Historically, most visualization tools have supported evaluation type decisions, where users compare options and make judgment based on predefined criteria. However, over the past 16 years, we've seen clear expansion in support for two dimensions. Construction type decisions, where users generate new solutions or new scenarios, and recognition primed decisions, which involve rapid experience-based judgment typically made by expertise. We believe this shift is driven by two major factors. The first is the increased complexity and uncertainty in today's decision-making environment. In such context, traditional decision models are often insufficient, and decision makers need to explore multi-scenario and design new plans, which may explain the growing support for construction-type decisions. The second factor is technological advancement. Improvement in real-time data processing, such as IoT system and visualization framework like D3.js have made it possible to support recognition primed decisions. So, the evaluation of visualization techniques reflect bold transformation in decision-making requirements, particularly at organizational and community levels. Our third key finding is that data visualization is gradually expanding its path to support toward semi-structured decision problems. Historically, visualization has primarily supported mostly structured problems. This pattern has been consistent from 2008 to 2024. However, since around 2012, and especially after 2020, we observed a clear steady increase semi-structured dimensions. The cross-analyzed scope and structure and user expertise show how this trend. Now, I'll present our answer to the research questions. Question 1, what type of decision problem has data visualization supported? Our findings show that data visualization primarily supports organizational and community level decision making, particularly for evaluation and construction, and recognition prime decision types. And question 2, focusing on a specific characteristic of decision-making problem, has support provided by data visualization changed over time? It's a type and structured. Question 3, if the characteristic of decision-making problem supported by data visualization have changed, then how have they changed with it is a reason of with advancement in visualization technology and changing social environment. And this is summary and almost died. Okay, it almost died, so I will end my presentation.
Okay. All right, so any questions? Go ahead.
Hello, thanks for the talk. Can you give an example of visualization problems along the dimension of structure? I'm curious, how do you distinguish between a semi-structured problem that's in decision-making versus an amorphous one? And is that distinction something that Franz and Kramer make, or is that your distinction?
Thank you, question. I need to show the another slide to you, like flexible framework and example. Okay, and I show you the later. I answered later and after presentation. Okay.
So you can have a discussion there. All right, so
All right.
one more question.
Maybe related questions. It is nice to see that visual analytics is being applied to more flexible form of decision making. Is there some technical driving force behind the trend that we are seeing more flexible form of decision making recently?
I think, thank you for question. I think, yes. Yes, I think the technical visualization technique like TCD.js or this system enable us to make decision making rapidly and efficiently. But recently, I don't think such example soon, and I want to discuss at this banquet. Okay.
All right, so let's thank the speaker again. Okay, the next speaker is Li-Chi Chong from Zhejiang University. Visual analytics of ball handlers' decisions in basketball games. It's a remote presentation. So can you switch to, yeah.
Yeah, thanks for the host introduction. Hello everyone, I'm Li Chen from Zhejiang University. Today, I'm glad to introduce our paper, Visual Analytics of Ball Handlers' Decisions in Basketball Games. In basketball, ball handlers is the player who controls the ball and responsible for making plays. The ball handlers can make one of three game-changing decisions. One, passing to a teammate, two, advising the ball by dribbling, or taking a shot right away. The ball handler's decision plays a crucial role in determining the offensive outcome. For example, both players start from a similar situation. The ball handler calls for a screen from a teammate. In the left video, the player shoots quickly after the screen but miss. In construct, the player on the right decided to keep dribbling to the basket, while leads to a successful play. However, most basic basketball states, like points or turnovers, usually focus on decision outcomes, making it hard to analyze the ball handler's decision-making in depth. Most existing basketball visual analytics mainly focus on game event narratives or summarizing tactical patterns, while player decision-making is not the central focus. There are also some works that focus on predicting or evaluating player decisions. But experts told us that analyzing historical data is just as important for building trust in the findings. To address this, we developed a visual analytics system that allows experts to explore different player decisions in similar game situations from past matches. Experts can draw tactical sketches to retrieve game segments with similar setups. The retrieval data is presented across 3 coordinate views, highlighting overall statistic, player-specific differences, and the impact of contextual factors. In close collaboration with basketball experts, we identified 3 key levels of decision analysis tasks. The first is helping experts locate the decision scenarios they care about, which leads to our first challenge, how to interactively explore historical decisions in a flexible manner. For the retrieved decision outcomes, experts need to summarize the statistics to form an overall understanding. However, the data involved in decision-making is highly diverse, including decision types, pass locations, and related game events. This brings us to the second challenge, how to enable visual comparison of multi-variable decision patterns. To support deeper analysis, it's also important to compare decision-making difference between players. However, for a specific offensive setup, the number of decisions made by an individual player may be limited, making direct comparison difficult. So we group players by their decision-making styles to enable more meaningful comparisons, which lead to our third challenge, how to quantitatively characterize decision-making styles. Finally, player decisions can also be influenced by contextual factors, such as score difference or time left on the shot clock. Exploring and comparing how these factors affect decision-making is also highly valuable. To help search for all decision scenarios under a specific offensive setup, we use the spatial indexing-based retrieval method. First, we transform the ball trajectory into a sequence of spatial chord regions. Then we aggregate these sequences over time to form our trajectory-based retrieval approach. Further details can be found in our paper. To support effective query input from experts, our sketch view provides a drawing area that mimics a tactical whiteboard. A user can select different types of trajectories from the tool palette and control the timing of each trajectory segment. This video demonstrates how an expert interacts with our system to search for similar offensive plays. The expert starts by sketching a tactical trajectory using the drawing tools providing the sketch view. They can control the timing and direction of each segment as they draw. Once the sketch is complete, the system automatically retrieves all historical positions that match this offensive setup. For all the retrieved similar situations, the player's decisions are extracted and summarized statistically. We use 3 colors to present the 3 types of decisions: and combine visualization to show the decision proportions and the average points across all retrieved situations. Finally, we use a radar chart to illustrate the specific game events associated with each decision type. In addition, some decisions involve spatial distribution information, such as where passes are typically direct. We use a grid-based matrix visualization to show these spatial patterns along with the corresponding scoring efficiency. For each group of players, their decision statistics are shown in a single row. At the far right of the row, we display how strongly each player's decisions are influenced by contextual factors. This part of the demo shows how users can browse through the decision statistics in detail. They can observe how decisions vary across different players and scenarios, and explore patterns in both decision types and their outcomes. To help users identify which players correspond to each role, they can browse the player groups in the player view. On the left, a scatter plot shows a 2D projection of the player's decision-making embeddings. The closer the point, the more similar the player's decision styles. To model players' decision-making styles, we draw inspiration from the idea behind word to back. The meaning of the word is defined by its corresponding context. Similarly, a player's decision-making style is determined by his decision-making context. We represent the decision context as a feature vector, including factors like game time and the spatial distribution of players on the court. Then, using a symbol-style architecture from word to vec, we input this context along with decision type and train the model to predict which player made the decision. After training, the hidden vector from the output layer serves as the player's decision-making embeddings. The projection of this embedding is shown in the fig. We can observe clear clustering based on player rules. For example, red dots represent guys who frequently handle the ball, while yellow dots represent centers who try to finish players near the basket.
2 minutes left.
Yeah, thank you. In this video, we show how users can explore the different players groups and make adjustments as needed, such as modifying group assignment or reviewing individual player details. Finally, through discussion with domain experts, we identified the key factors most likely to influence player decisions, including time, defensive pressure, and score difference. We use chi-square test and p-values to quantify the influence of each factor. In the factor view, two coordinate charts are used. A line chart shows how decision outcomes vary, and a static bar chart shows how decision tendencies shift across different levels of a selected factor. This video demonstrates how users can explore and interact with the factor view. We evaluate our systems through 2 case studies using the real game data in close collaboration with professional basketball experts. This case study helps us assess how well the system supports in-depth decision analysis in real-world scenarios. After the case study, the domain expert provided valuable feedback and suggestions. They appreciate the novel perspective our system brings to decision analysis, especially the sketch-based whiteboard design. They also suggest that adding standard template could help simplify the process of detecting game situations. To sum up, we propose a learning framework for modeling decision-making styles and a VA system for multi-perspective analysis. In future work, we'll explore overboard decision-making and sport team collaboration analysis in sports like basketball and soccer. We thank the funding agencies for their generous support. That concludes my presentation. I'm happy to take any questions. Thank you.
Okay, so we have time for one short question.
Yeah.
Any questions from the audience? All right, so let me ask a question. So which part of your system was specialized to basketballs? I think the designs of many components are quite general, so it can be applied to different team sports.
Yes, this system actually can be adapted to broader team sports like soccer. After reasonable modification to the sketch panel and the search engine, they can be applied to search for similar game situations in soccer. Since decision making in soccer, like player locations, score defenses, and the defense context shares similarity with other sports analyzed. The representation learning method used would also characterize soccer players' decision-making patterns effectively.
All right, thank you very much. So
Yeah,
let's thank
thanks.
the speaker one more time. And our last speaker is Ko-Chih from University of Massachusetts, Boston. And the title is Evaluating Graphical Perception with Multimodal LLMs.
Hello everyone. My name is Ko-Chih Maeda, and I'm a undergraduate student at the University of Massachusetts, Boston. Unfortunately, the first author, Rami, cannot be here today, so I'll be presenting on her. This is my first time attending a conference, so I'm really excited about this opportunity. Anyway, the research I'll be sharing today is evaluating graphical perception with multimodal large language models. Our work builds on the famous graphical perception study by Cleveland and McGill from 1984. Graphical perception here means the human capacity to interpret information on visualizations such as charts or graphs. They conducted these experiments testing how accurately humans can read these visualizations. In 2018, Han, Tomkin, Pfister extend this work to convolutional neural networks to see how well these models can perform on the same experiment compared to humans. And here are the actual experiments they conducted, all of which fundamentally followed the 1984 human graphical perception study. This is a really quick overview. This is the first experiment, which consists of 9 elementally perceptual tasks. So it ranges from angle to, for example, like direction. And there are some examples that involve reading pie charts and bar charts. So these are the examples. And there's also experiment that assesses dot counting accuracy. I will go into details shortly. We now extend this work to multimodal large language models. As you know, a key characteristic of these models is their ability to read or process multiple data types, not only text, but also images, audio, and maybe more. There are many models out there, and of course, ChatGPT is one example. Its performance is very eye-opening, but we know that they also have some limitations. So that motivated us to investigate how well multimodal large language models can perform the aforementioned graphical perception tasks at this point compared to humans. To evaluate the performance, we follow the same experimental design and setup as in the previous studies. We used binary aliased images with a black background and some noise. Zero-shot prompting. Zero-shot prompting is the method we use to create the models and retrieve the responses. Zero-shot prompting means a model performs the task without prior knowledge or examples, so they do not know the stimuli or expected answers beforehand. Here's a quick overview. Here's a quick example from the angle task. So we provide an image with the following prompt. Estimate the angle, number only, no explanation. The model then returns an answer, for example, 70. And to quantitatively assess their performance, we used the mid-median logistic absolute error, because this calculates errors, a lower MLE indicates better performance. And here are the models we evaluated in this study. For the pre-trained models, we selected GPT-4, Gemini 1.5, Gemini Pro Vision, and Llama 3.2 Vision Instruct. These are all widely used models with multimodal abilities. Additionally, we also fine-tuned Llama specifically for this study. And by this, we aim to see how fine-tuning affects the performance of the models. And here are some numbers for fine-tuning and evaluation. We made sure each data set had unique labels, or I should say, unique images. And for human baselines, we used data from the previous studies. Since the time is limited today, I will focus on a few selected experiments and share the results. This is experiment 1 again, and it's about elementary perceptual tasks where subjects are asked to estimate the encoded numerical values. So for example, in the angle task, the models are asked to estimate the size of a given angle. And here is the results of the curvature task. As you can see, all models outperform humans. But in the angle task, they slightly underperformed humans. Now the situation is reversed. Humans actually estimated more precisely than the models. So this suggests that for elementary perceptual tasks, performance of the models depends on like the specific task. Let's move on to the next experiment, the position angle experiment. In this experiment, the models are asked to estimate the ratios of these 5 segments. And our result shows that our models greatly outperform humans in both chart types. As a side note, the previous studies showed that bar charts are more readable than pie charts, at least for humans. And we saw some longer bars in the pie chart result, which might explain the difference. And let's skip the last experiment, experiment 5, which is the point cloud experiment. In this experiment, a model is shown an image with an initial set of dots, 10, 100, or 1,000, plus some additional dots. So the task here is to estimate the number of the additional dots. And this experiment becomes more challenging as the number of the initial dots increases from 10 to 100 or even 1,000. Even so, all models answered more accurately than humans across all cases. So here's a quick conclusion. While humans still excel at certain tasks, we saw that multimodal large language models outperform humans in the majority of the experiments we conducted. So if I were to give one key takeaway, that would be that multimodal large language models have promising potential for graphical perception. Of course, there are many more models out there, and there are many more visualizations that need to be tested, and that will be our future work. And that's all for my presentation. Thank you very much.
All right, so any questions from the audience? No question? So I have a couple of questions. So so I wonder if you draw something different, some novel insights compared to the previous study on the CNN models. I mean, what is something you found through the study on the graphical perception models?
Oh, well, basically we replicated the 1984 and 2018 studies to see how multimodal large language models perform like compared to humans. So so the conclusion we got is so humans still work better in some cases, but overall multimodal large language model outperform like humans in the experiments we conducted. So we didn't compare the performance between.
All right. And have you investigated the effect of prompts? For example, if we ask them to try the
Even prompt engineering.
yeah, or do some role playing, do they work better?
Oh, well, we did some prompt engineering studies. We read some papers, and the consensus is that like the detailed guidance can lead to better performance. So for all experiments, we follow the same format, estimate something and the correct range or an invalid range, number only no explanation. And that way, models can know what to answer, how to derive numerical answer.
Okay. Okay, that's it for today, and we can the general chair will come soon, I think. For a couple of minutes so that we can announce the location or the next schedule. Thank you very much.
After we finish here, we can head down. Everyone who is going to the banquet can go to Chiang Kai-shek Memorial Hall, the MRT line, and to exit 5. Yeah, so we're wrapped up here, and anyone ready to go, go downstairs and look for further guidance on which direction to walk. Take the MRT to Songshan Station and get off towards Songshan, and then get off at station.
Just like go downstairs and walk to the Chiang Kai-shek Memorial Hall station. Take the green line. Okay, take the green line to the right direction. Okay, to the Nanjing Fuxing station. Okay, and the exit from the exit 6. Okay, then just walk for 1 minute. Then you will see the China Park with the PacificVis banner there. Okay, so if you don't know like the detail, okay, cannot remember, I sent an email this morning. You can find it, or like on our website also have those instructions. Okay, yeah, thank you very much. Yeah.